Okay, this video is to finish up the notes from yesterday on sampling distributions for the difference of sample means. If you were not here yesterday, due to the WorkKeys ACT, the substitute does have a copy of the notes for you, so just ask her for it. And the notes from yesterday have been uploaded into Canvas, so take a moment to pause this video and go and copy those notes down. All right, now that you got the notes for the first part of the notes from yesterday's version that was loaded into Canvas, let's go ahead and complete number 3. So the distribution of ocean wave height at a certain California beach is approximately normal with mean 7.2 feet and standard deviation 0.98 feet. The distribution of ocean wave height at a certain Florida beach is approximately normal with a mean 6.6 feet and standard deviation 1.2 feet. 6 waves from each beach will be selected at random and the heights will be recorded. What is the probability that the sample mean for the California waves minus the sample mean for the Florida waves will be greater than 0.5? In other words, what is the probability that the sample mean for the California waves will be 0.5 feet higher than that for the sample mean of the Florida waves? So let's go ahead and get started. So number 1, we are talking about a sampling distribution for the difference of sample means. So let's go ahead and get some notation down with the values that we have been given. So let's start back talking about the waves at the beaches. All right. So the distribution of ocean wave height at a certain California beach is approximately normal with a mean of 7.2 feet and a standard of 0.98 feet. So these are population values. So if I take a look at these, I'm going to have mu, and we'll use a C for California. Let's use a capital C. There we go. So the population mean wave height for the waves at this particular California beach are going to be 7.2 feet. All right, so that's for the waves on that California beach. And additionally, the standard deviation for the waves on this California beach is going to be equal to 0.98 feet. So that's the waves from the California beach. So those are those first 2 values. Now, I also want to do the same thing for the waves from the Florida beach. So the mean wave height for the waves on this Florida beach turns out to be 6.6 feet. And the standard deviation for the wave height for the waves on this particular Florida beach are going to be, or is going to be, 1.2 feet. All right, so here's our notation for those first numbers. Those are for the first values. This is for the population of all waves on these particular beaches. We've got the average height, or the mean height, and we've got the population standard deviation. So now we want to turn this thing into a sampling distribution in a difference of sample means. And it tells us that 6 waves from each beach will be selected at random. So that means I can add to this information here for my California beaches, and I can say that, well, N sub C, that is the sample size for the waves from the California beach, is going to be equal to 6. And that's also going to be the same thing for my Florida beach. We are going to have a sample of 6 waves from this Florida beach. So N sub F will also be equal to 6. Now, when I turn these into a sampling distribution, I know from an earlier study, when I look at a sampling distribution of simply sample means, I know that the sampling distribution, or the mean of the sampling distribution of the sample means, that is still a mouthful. So in other words, mu sub x bar of C It's just going to be equal to the population mean. So this is still going to be equal to 7.2 feet. All right. So the mean of my sampling distribution of sample means is the same as my population mean. We looked at that as to why before, because it is an unbiased estimator of the population mean. However, my standard deviation of the wave heights from this California beach, and that this is just for those 6 waves that were randomly selected, is a little bit different. So for that, what I have to do, remember, our formula for it, is to take the population standard deviation, 0.98, and divide it by the square root of my sample size. And so if I do this, if I go to my calculator, let's see, where's my calculator at? Here we go. I've got 0.98 divided by the square root of 6. And let's see, we're going to get a standard deviation of about 0.4, well, I'm going to say 0.4. Okay, it's approximately 0.4. Now we need to also do something like that for the wave heights, for that sample of wave heights from the Florida beach. And so if I was to build a sampling distribution of sample means from all the random samples of size 6 from that particular beach in Florida, what I would be looking at is very similar to what we did here. I would say mu of x bar. In other words, the population mean of all of the samples of size 6 from this Florida beach is just going to be equal to the population mean. So here it would be 6.6 feet. And then what I would have is similarly, I will calculate the standard deviation for this sampling distribution of sample means, similar to what I did for the California beach. So again, I'm still going to have, let's see, it'll be x bar sub f. And I have to take my original standard deviation divided by the square root of my sample size, which again was 6. They were taking 6 waves from each beach. And let's see, that is going to be approximately, let's see what I come up with, 1.2 divided by the square root of 6 again. And we get about 0.4899. So this one has a little bit more variability, these waves from the Florida beach. And again, this is still in feet. I didn't note that on the ones from the California beach, but this would still be in feet. So let's add that over here. So this is in feet. Okay. So now I have not only my population parameters for each beach, so these would be my population parameters for each beach. Let's see if I can get it to draw this here. There's population parameters for each of the 2 beaches. Well, let's see if I can get it to draw it properly. And then I also have my statistics for my sampling distributions. Or I guess it'd be my parameters for my sampling distribution, I should say. And so these are the things for my sampling distributions of sample means. So what I want to do now is I want to take this information and I want to calculate the probability that the difference in this would be more than 5 between the average wave height for the waves selected from the California beach minus the average height for the wave selected from the Florida beach. So while I have parameters for individual sampling distributions, now I need to come up with parameters for my combination here, or my difference. So when I do this, what happens is if I look for, let's see, what's the first thing I want to do? I want to find my center. So I'm going to go ahead and calculate mu sub, and we'll do x bar, sub f. And I want to find the mean of the difference between these two. So I'm going to say minus, and then I'm going to have sub, let's see, minus, and then we will do bar X, and then this would be, whoops, the first one should be the California beaches, not the Florida beaches. This one will be the Florida beaches. And so when I do that, it turns out that all this is, it's just the difference between the actual two population standard, or not standards, means. So this is just going to turn out to be 7.2 minus the 6.6, which is going to give us a 0.6 feet. So that's our average difference between the waves. If I took every sample of size 6, this would be the average difference in heights between the waves on the California beach and the waves on the Florida beach. Now, in addition to the center, I also need to know the spreads. That means I need to find the standard deviation for this difference, this sampling distribution of the differences of the sample mean. So let's do that next. So now I'm going to be looking for sigma, and I'm going to be looking for it for x bar sub c minus x bar sub f. All right, so I'm looking for that standard deviation here. And as we discussed yesterday in class, when we do this, remember we have to use the variances. We cannot use the individual standard deviations and do a combination that way. I have to use the variances, but I will be coming back to these individual numbers here. So remember, for any combination, I always have to, for standard deviation, I always have to add. Even though I'm finding a difference, I have to add. And so what we're going to do is we're going to end up taking that standard deviation for the 6 waves, or the sampling distribution for the 6 waves from the California beaches, and I have to square it to get my variance. Now, the reason I don't take the square root here of the sample size, as we discussed yesterday, is I'm actually squaring this entire fraction. So I'm squaring the numerator, but when I square the denominator, the square root and the square are inverse operations, and basically they just cancel each other out. Then I'm going to plus. Even though I'm subtracting, I'm finding a difference. I'm going to use a plus. And so now what I have is I need to take the 0.4899. That needs to be squared, and it also needs to be divided by 6. And so we're going to take and find that this is approximately, let's see, we've got the square root of 0.4 squared divided by 6 plus, then we're going to take 0.4899 squared divided by 6, and I need to know what this value is. And it turns out that the standard deviation of the sampling distribution in the difference of the sample means for the two beaches is about 0.2582. So 0.2582. And again, this is going to be measured in feet. So this gives us the parameters for our sampling distribution of the differences in the sample means. All right, so now we have the parameters for that sampling distribution of the sample means. So now I'm going to go ahead and check my conditions. All right, so we have 3 conditions when I'm trying to do probability here. Number 1, let's see, number 1 was that we used simple random samples. So a simple random sample, or an SRS, of 6 waves was collected from each beach. And then their heights were measured. The next one is to check to see if it's independent. So they took 6 waves from each beach, so 6 times, or 10 times 6, would give us, that would be equal to 60, which is definitely less than all waves on the beach in California, and all waves, and I'm going to say and, let's do it again, 10 times 6 is equal to 60, is less than all waves on the beach in Florida. So So this is establishing independence, which basically just tells us that we can use that standard deviation that we just calculated in the box above. And then finally, I want to show that this thing is approximately normal in shape. And that's what's going to allow us to use our normal CDF. So the way I'm going to do that is, if you remember up in the passage, it told me that both populations were approximately normal. So because the shape, I'm going to say the shape is approximately normal because both distributions, both populations, I should say, both populations, so I want to be clear on which distributions I'm talking about. Both populations were normally distributed. Now remember, if we didn't know that, we would be relying then on the central limit theorem, and that would be that the sample sizes are at least 30. All right, so now that I have all of that, I'm going to go ahead and sketch out my distribution. All right, so I'm going to make a picture of it. And I also want to state the parameters for my distribution, so let's come along and do that. So, because we're not going to make all three standard deviations in here to show that it follows the empirical rule, so instead I'm going to say that it's normal with a mean of 0.6 feet and a standard deviation of about 0.2582 feet. And so they're the parameters for this. And so I'm going to go ahead and draw my center in. I'll draw the center in here at 0.6. Let's see, I'm going to have 0.6 right here. And then it says that we want a difference of greater than 0.5. So I'm going to come over here and put a line in for 0.5. Now, my one standard deviation is 0.2, so that would take me down to 0.4. So I'm thinking 0.5 is actually going to be somewhere more like right in here. All right, we're going to say that it's somewhere like more right in here. And so that's our desired value. So what we're going to be doing is we're going to be shading to this side here. We're shading in, no, I'm sorry, they want it to be greater than. We're not going to shade to the left. We're actually going to shade to the right. Okay, so we're going to be shading to the right. We're going to be shading, oh, okay. Get the screen to stand still. We're going to be shading this way here. We're looking for greater than. Let's get those erroneous lines out of here without deleting my normal curve, hopefully. There we go. Let's see if we can do that. There we go. And so now we just need to make our probability statement and use our normal CDF. All right. We just need to make our probability statement and use our normal CDF. So this here was 0.5. I'm going to pause the video for a moment because the bell's about to ring, and I'll resume the video shortly. All right, so now what we need to do is make that probability statement and conduct our normal CDF. We've met all of our conditions. We've calculated our parameters for our sampling distribution. So now it's time to do that probability statement and the calculations for it. So we're looking at the probability that x bar sub c, that is that the average height of the California waves, the 6 that were randomly selected from California, are 0.5 feet more than the ones that they observed or selected, randomly selected in Florida. And so again, this is the same notation that they used above, and this is the question that was asked. All right, x minus x bar sub c minus x bar sub f is greater than 0.5. And so we're going to go ahead and talk about or do our normal CDF calculation. So I've got my curve up there, I've got my parameters, we checked our conditions, so now we're going to say, well, we'll say normal CDF, and we're going to go ahead and get started. So I've got my lower bound. Well, my lower bound here would be the 0.5, because they asked what's the probability that it would be more than that. My upper bound then technically would be positive infinity. But again, on your calculator, you'll use a 9999, a lot of nines. And then our mean, mu, for our sampling distribution here was 0.6. And then finally, our standard deviation for our sampling distribution was 0.2582. Now, what I need to do is go to my calculator and see what value this gives us. All right, so let's do that right now. So I've got that normal CDF in there. We're going to go ahead and enter it in our calculator. And so I'm going to do normal CDF. That's number 2. We are setting 0.5 as my lower bound, setting my upper bound to several nines. My mean was 0.6, and let's see, our standard deviation again was 0.2582. So we're going to do 0.2582. And here's our probability. It's about 0.651. So our probability here is 0.651. 0.651. And that answers that question. What is the probability that the difference in average wave heights is greater than half a foot, or 0.5 feet? Okay. So that probably turns out to be 0.651. And that's it for the video. So I hope this helps with understanding how to use a sampling distribution of sample means. And again, I will answer questions on Friday. Well, tomorrow. Until then, I will see you all later.